Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Bridge Design to Improve Sustainability and Life Cycle Costs. My name is Amanda and I'll be your host for today. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Magiba. Magiba is a Swiss company with its head office in Ballack, north of Zurich. It was established in 1963 and ever since has become one of the world's leading suppliers of structural bearings, expansion joints, seismic protection devices, and structural monitoring systems for infrastructure, buildings, and industrial structures. To date, they supply high-quality products to over 25,000 structures around the world. With locations worldwide and 5 production facilities in Slovakia, Hungary, Turkey, China, and India, Magiba is a successful and consistent global player in the industry. These certified production sites ensure optimal control of quality, timing, traceability, and social responsibility, and provide even better market coverage and reaction to their customers' needs. Today, we will hear a keynote presentation, followed by a panel discussion and our live audience Q&A. And as always, I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Mark Bennett. Mark is a veteran bridge and structural designer with several decades of experience with Transport for New South Wales and now with Oricon. Mark has been a strong supporter of the technical innovation in the bridge industry and has been the chair for Code Committee BD 90.4 for critical improvements. Please welcome Mark Bennett.
Thanks for the introduction. Good morning, everyone. In today's presentation, I will provide an outline of the provisions of AS 5100.4 for the selection and design of bridge bearings and deck joints with the aim of achieving sustainable bridges with long service lives and minimum maintenance requirements. To this end, one design approach is to minimise the number of deck joints and bearings in a bridge. However, except for short length bridges, most bridge types require the use of some bearings and deck joints. The standard covers 5 types of bridge bearings: plain and laminated elastomeric bearings, conventional pots, high-performance pots, and spherical bearings. For plain pads and elastomeric bearings, the standard provides comprehensive design rules. For other types of bearings, for the pots, high-performance pots and sphericals, it just provides primary design and fabrication provisions only. It also includes some provisions for older bearing types, including rockers and rollers. The notional design life of bearings and deck joints is set as 50 years, except casting components, which should have the same design life as the bridge, and easily replaceable components such as deck joint seals that can have a shorter design life. One of the oldest installation of rubber pad bearings is in Melbourne on the railway viaduct between Flinders and Spencer Street Station. This bridge was constructed in 1889. A sample of these bearings was tested in 1980 by the Malaysian Rubber Producers Research Association. The rubber hardness was measured at 63 and degradation was found to be minimal. It was concluded that the rubber bearings are still function satisfactorily after more than 100 years in service. However, defects and damage can occur in laminated elastomeric bearings. This photo shows some strange exfoliation of the rubber, which I've seen on a couple of bridges, and also you can get splits and delamination. Elastomeric bearings are designed for serviceability limits data set. This photo shows a cross-section of a laminated elastomeric bearing. What you're looking for is nice uniform layers of rubber with parallel steel plates. In this bearing, the side cover is a bit deficient and the corners of the steel plates should be rounded. Failure modes include splitting of elastomer and delamination of the elastomer from the steel plates. Normally the stress occurs over time due to cyclic loading. The bearings have significant reserve capacity for infrequent extreme events. So a bit like fatigue, the design of elastomeric bearings is carried out at SLS. Select elastomeric bearings over pot and spherical bearings if the load and movement range allows. They are cheaper and more durable than other types of bearings. The vertical load capacity is controlled by a number of criteria. The first is total shear strain, and you're actually calculating the strain in the rubber at the bulges between the steel plates. There's a general stress limit of 15 MPa, and there's a stability limit, bearings can undergo shear buckling as opposed to flexural buckling. The shear deflection capacity is set with a maximum shear strain of 0.05, which corresponds to half the total rubber thickness of the bearing. However, for infrequent loads, elastomeric bearings have a much larger shear deflection capacity as demonstrated in this capacity. Therefore, clause 12.6.3 states that brake and earthquake forces need not be considered for the application of the shear deflection limit. The bearing equations are based on full contact over the full face of the bearings. A problem that still occurs too often is gaps in the contact surfaces. Gaps at intermediate construction stages are not a problem. There just needs to be no gap under permanent effects and service load effects. Dimensions of tapered attachment plates need to be accurate. Bearing selection needs to be appropriate. For girders erected onto bearings, clause 7.5 requires consideration of construction tolerance, rotation tolerance allowance of 0.005 radians. This limit can be exceeded if the tolerances on individual items are combined, so a good standard of workmanship is required. The standard provides bearing performance tables for standard bearings. Where possible, bearings should be selected from the range of standard bearings. Most of the calculation of work done for bearing selection is done in these tables. A bearing is identified by an AS part number. This consists of the rubber hardness in square brackets. The next two digits are the plan size, indicate the plan size of the bearing. The middle two digits indicate the rubber layer thickness, and the last two digits are the number of internal rubber layers. The bearing performance tables provide the compressive, shear and rotational stiffness of the bearing, the shear deflection capacity, and it provides the rated loads at 0 shear and 0 rotation, 0 shear and 0.01 radians rotation, maximum shear and 0.01 radian rotation, and the minimum load to achieve a 0.005 rotation. Good bearing selection can be made by just referring to the table. With the rotation tolerance allowance of 0.005 and the live load rotation is typically 0.003 or 0.004 radians, the 0.01 rotation limit provides a good boundary of the upper rotations that the bearing will undergo. So just by comparing the rated load at 0 shear and the rated load at maximum shear is the operating load condition of the bearing. It's recommended that bearings be selected working from the bottom of the table up, picking the lowest height, picking the bearing with that has the required rated load capacity and shear deflection capacity. This is a copy of the tables taken directly from the standard. The bold numbers are an indication that this bearing doesn't provide for a 0.010 radians capacity, rotation capacity, and the shaded area is an indication that the buckling capacity is the limit on the vertical load on the bearing. This chart indicates the effect of rubber layer thickness on rotation capacity and load capacity. So if we are looking at rotations past 0.01 radians, we can see that the 07, 09, 05 bearing has very little operational capacity. If the rubber layer thickness increases to 12 millimeters, there's a reasonable operational area for the bearing performance, and increasing to the 15 millimeter internal rubber layer, you can see the rotation capacities are a lot greater, but the rated load capacity does drop off. Bearing restraint. There were two requirements for bearing restraint. The first equation is a straight friction consideration. So for a bearing deflected to its shear capacity, equation 1 gives a coefficient of friction about 0.17 or to 0.20. This photo shows a bearing sheared to 50% shear strain. The second photo shows the bearing sheared to 100% of the shear strain. When a bearing is subject to shear deflection, the bottom rear corner of the elastomeric bearing curls up. Then with thermal cyclic loading, a caterpillar type action can occur in the cover layer of the bearing that results in the bearing walking out of position. To prevent this, a minimum clamping force needs to be applied to the bearing. To prevent walking, a clamping pressure of 2.2 MPa needs to be applied to the bonded area of the bearing. If the clamping force is not available, then mechanical restraints need to be provided at the top and bottom faces of the bearing. There's been a range of different bearing installation details used over the years. A tapered machine plate is an acceptable attachment plate for an elastomeric bearing, but in New South Wales the common practice is to use a pre-moulded epoxy mortar pad bonded to a steel plate as the top attachment plate. With this arrangement, it allows the taper dimensions to be varied to just a few weeks before girder erection if the measured hogs don't match the predicted hogs. So this is a photo of a standard bearing installation that's done in New South Wales. The tapered pre-moulded epoxy mortar pad with the steel plate that's screwed and that's bolted and glued to the soffit of the girder. There's keeper plates that are bolted onto the top attachment plate. The bottom mortar pad should be detailed to extend at least 50 millimeters past the face of the bearing, so that a minimum of 25 millimeters will be achieved, accounting for construction tolerance. Don't construct mortar pads using proprietary non-shrink grout. These shrinkage compensated grouts that include expansion agents to compensate for shrinkage. Often they have a two-phase expansion during setting and during initial strength gain. The unconfined mortar pad can end up with undulations or doming in the top surface. Also, they often have no coarse sand, so end up being very smooth. For bearings that don't have adequate clamping pressure, mechanical restraints are provided top and bottom, and there needs to be allowance for construction tolerance along girder length. Elastomeric bearings should be installed horizontal. There are two exceptions to this rule. Bearings can be installed in inclined pairs. This allows a component of the higher compressive stiffness of the bearing to be accounted for to increase the shear stiffness of the support. This is rarely used. A couple of examples are the Sydney Airport International Terminal Departure Viaduct and the bridge over Lake Ginninderra in Canberra. For short span bridges and small bearings, it is acceptable to install the bearing on the incline, but the bearing needs to be mechanically strained top and bottom, and the self shear needs to be small. If you do install elastomeric bearings on the incline with no mechanical restraint, they can quickly walk out of position as shown in these photos. Also, if the clamping force on the bearing is too small, but it does have a top attachment plate, then the bearing can, rather than shear, can slide back and forth over the top of the mortar pad. If the shear capacity of your elastomeric bearing is too small, you can incorporate a sliding plate interface on the top of the elastomeric bearing. The thing to note with this approach is that the coefficient of friction of sliding surfaces is pressure dependent, and that the pressure allowed on sliding pads is a lot higher than the pressure allowed on elastomeric bearings. So to get a low coefficient of friction, you should make your sliding pad quite a bit smaller than the elastomeric bearing. Strip bearings are invariably placed on an incline, so should be mechanically restrained. So just summarising for elastomeric bearings, select elastomeric bearings over pot and spherical bearings if the load and movement range allows. Rectangular bearings are cheaper per kilonewton. Specify circular bearings for bridges with high skews, curved alignments, or where girders splay out. If movement range exceeds shear deflection capacity, consider using shorter deck modules, reduce distances between expansion joints, or incorporate a sliding plate on bearings. When selecting bearings from a table, start from the bottom. Larger rubber thickness and taller bearings provide larger rotation capacity. Don't select oversized bearings. Check pressure on bearing to determine fixity requirements. Install bearings level unless special conditions are met, and provide mechanical fixity to strip bearings. Conventional prop bearings have been in use for the last 50 years. They consist of a pot with a rubber disc inside, a piston plate, and there's internal seals. So in the past, these internal seals used to be metal rings, and with the millions of cycles of rotation, the metal rings used to wear the sides of the pot, and under high pressure, the rubber can shred and extrude from the pot. So these days, the use of POM chain plastic seals vulcanized into the rubber pad are normally used. Another interesting feature is that where you have a sliding interface using a polished stainless steel sheet, it should be welded to the backing plate to prevent interface corrosion. Unfortunately, in years past, stainless steel sliding sheets were just attached using countersunk screws, and there's lots of bearings with very bad interface corrosion occurring. There's a new generation of pot bearings, high performance pot bearings. They use the rubber pad with the POM chain seal, and they use an advanced sliding material, sliding surface, not Teflon. So in this case, this is ultra high molecular weight polyethylene. The sliding surface is dimpled to provide lubrication reservoirs in the top of the bearing. And with these features, the pressure allowed on the rubber pad and the pressure allowed on the sliding surface can be a lot higher than for conventional pots. A new generation of spherical bearings is also available. This incorporates the advanced sliding material on the conical face and any associated sliding surface. Bearing subject to uplift. The form, articulation and span lengths of the bridge should be selected to ensure the bearings are subject to compression under all load effects. Obviously, for elastomeric bearings, can't be subject to uplift at either SLS or ULS limit states. For pot and spherical bearings, the stand allows uplift at ULS, but not at SLS. And as you can see from this photo, the bearing subject to uplift is much larger and taller than a standard pot bearing. Sliding contact surfaces. So the maximum pressure allowed on PTFE at ULS is 60 MPa. There's new advanced sliding materials, typically ultra-high molecular weight polyethylene or fluoropolymers that have a maximum pressure allowance of 120 MPa, but that limit is temperature dependent, and the pressure is calculated on an effective contact area. This photo shows an old style PTFE sliding surface. In the past, the PTFE wasn't dimpled. If the pressure is excessive, then the PTFE can extrude, or there can be shavings of PTFE can get shaved off the Teflon disc. So a commentary to the latest version of AS 5100.4 is currently being prepared, and a new template for the bearing performance schedule for pot and spherical bearings is being proposed. With this layout, the movement shown on the schedule should include the additional plus or minus 25 millimeters required by clause 2.5. The rotation shown on the schedule is the vector sum of the rotations about the longitudinal and transverse axis of the bridge, increased by an additional 0.01 radians rotation allowance required by clause 7.5. Where the maximum and minimum vertical loads concurrent with horizontal loads are the same as the general maximum and minimum vertical loads, the concurrent vertical loads need not be shown. Where uplift at ULS occurs, an additional column should be added to the schedule showing the minimum SLS vertical load on the bearing. To minimise the risk of construction errors, where the difference between the longitudinal expansion and contraction movements is less than, say, about 40 millimeters, it is reckoned that the movement range be shown as plus or minus the largest movement to avoid the need for a preset. Where different load combinations result in significantly different concurrent maximum horizontal loads with minimum or maximum vertical loads for a single bearing, multimate load sets can be shown on the schedule for a single bearing. Bearings or bearing load sets where friction can be accounted for in the calculation of anchorage capacity of the bearing should be indicated. The required cube strength of mortar pads and the maximum pressure on the reduced effective area at the interface of the attachment plate and mortar pad should be shown on the bearing drawings. A maximum value of 55 MPa is recommended. For bearings with an advanced sliding surface, the maximum operating temperature of the bearing should be shown on the bearing drawings. As a guide, the maximum air temperature -4 degrees is recommended. Pot and spherical bearing catalogues. Pot and spherical bearings are custom designed for the loads and movements provided in the bearing performance schedule. The bearing catalogues give an approximate indication of the size of the bearing. However, stainless steel bearings will be substantially larger than structural steel bearings. If the ratio of horizontal force to vertical force is high, the bearings will be larger than shown in the catalogue. Bearings that need to resist uplift will be significantly larger and taller. To allow for variation in bearing dimensions, it is recommended that pot and spherical bearings be installed on a reinforced concrete plinth whose height can be adjusted. Also, it's recommended that a trial grouting of an attachment plate be carried out to confirm the suitability of the proprietary grout and the grouting methodology before installing the bearings. To allow for the higher pressures from high performance pot and spherical bearings, load limits for reinforced concrete substrates are provided. These are higher bearing limits than in AS 5100.5, which are for unreinforced concrete substrates. The reinforcement for these reinforced concrete substrates need to be designed using strut and tie or pre-stressing anchorage, detailing design requirements. So just to finish up, some final words on deck joints. In AS 5100.2, the ultimate braking forces are much higher than in other bridge codes, including AASHTO and the Canadian Bridge Code. For this reason, it's specified that deck joints be designed for ultimate limit state movements due to temperature creep and shrinkage and SLS braking movements. On the basis that strip seal joints can overextend and close up without damage, for strip seal joints it's permissible to ignore braking movements. But the deck joints also need to be designed to accommodate any foundation movements that may occur. The standard provides provisions for 5 types of deck joints: strip seal joints, sawtooth joints, finger plate joints, flexible plug joints, and modular joints. This photo shows a modular deck joint with noise reducing plates on the top. Modular joints are expensive mechanisms and should only be specified where other types of joints will not work. That's the end of my presentation. I hope you found that useful. Thank you.
Thank you, Mark, for a great presentation. I'd now like to welcome our second panellist for today, Mahesh Ramamurthy. Mahesh has been involved for over 25 years in the design of many bridge designs internationally and in Australia and New Zealand. He is also a very proactive contributor to critical improvements of the AS 5100.4 for several years. Please welcome Mahesh Ramamurthy. I'd now like to welcome our final panellist, Virendra Godke. Virendra is a civil engineer with over 18 years' experience in engineering structural connections, especially for bridges and other critical infrastructure. He has also been actively contributing towards the critical improvements of AS 5100.4 and is a staunch supporter of technological improvements to achieve sustainability. Please welcome Virendra Godke. Thank you. Today, we will hear from our 3 panellists in a discussion, followed by an audience Q&A. And as always, I encourage you to send questions through to our speakers via the YouTube chat box. I'd now like to start off today's panel discussion with Virendra. Virendra, I'd like to sort of pose a couple of questions to you around early design decisions and longevity. How can early stage design choices, particularly in selecting engineered bearings and deck joints, impact the long-term durability and performance of bridges? Virendra.
Yeah, thanks, Amanda. The critical aspects of selecting the bearings and deck joints are obviously the durability and maintenance, the load distribution and structural integrity, environmental resistance, and at the same time the cost efficiency over the life cycle, the whole of the life of the structure itself. How is it critical? If we miss one of these aspects to consider while selecting the bearings at the early design stage, not only we will have detrimental impacts on either durability or the structural integrity, or the environmental resistance of the bearings and overall on the entire structure. But at the same time, it could be a very costly exercise to either maintain or replace these bearings and structure deck joints over the life cycle, over the life of the structure. At the same time, during the construction, if the early design decisions were not made in consultation with the bearing manufacturers, the construction can be quite costly against the budgeted construction cost. The examples of that would be, there will be several clashes of the bearing anchors with the reinforcements. The bearing would not fit into the given area. So these are some of the reasons why the early stage design choices needs to be made considerately and in consultation with the bearing and deck joint manufacturers.
Thank you. Thank you for that. And just staying with you, Virendra, for now, can you share examples where early design decisions either significantly extended or compromised a bridge's lifespan? Thank you.
Definitely. I'll start with a couple of examples, but I think Mark could also share some examples. So the examples of the detrimental impact on the longevity or the maintenance issues of the bearings and deck joints. Obviously, the bearings that were designed without having attachment plates, M7 viaducts in Sydney are the best example. There's also the Westgate Bridge in Victoria that had an expansion joint selected. It's kind of a old technology roller shutter joint, which proved to be very very costly to maintain. Um, the good examples would be obviously the ones that would enhance the life and reduce the maintenance. The modular joints that were installed on the Gateway Bridge in Brisbane originally in 1984, they lasted quite long without too many maintenance issues. At the same time, another example of the early design choices going wrong is use of metal internal seal pod bearings onto the railway bridges, especially the steel girder bridges, where the pod bearings with metal internal seal have proven to fail within 5 to 10 years, which is very very short considering their expected lifetime. And then the replacement exercise would have been very very expensive. Um, we we have replaced hundreds of those bearings especially in Western Australia, and hundreds more to go. um, Mark, would you mind sharing your experience on the M4 viaduct and Alfred's Point, where there are some issues with the expansion joints?
So look, some finger plate designs have deck joints are subject to high fatigue loads, and sometimes the fatigue detailing of finger plate joints and other types of joints hasn't been the best. So there has been failures of finger plate joints, especially. So yeah, look, if there's an associated bedding plate, they need to be all properly detailed for design. And look, the problem of rubber shredding or like extruding from pots that have used brass or bronze sealing rings, that's an ongoing issue. And look, bearings that were manufactured using countersunk screws to fix stainless steel sheets. Unfortunately, there's a legacy in New South Wales of lots of pot bearings with extensive interface corrosion. So the current specification and the standard specifies that the steel plate needs to be welded to the backing, to a structural steel backing plate.
Thank you for that, Mark. I'd now like to move on to talk about standards and best practices around AS 5100.4. Mark, the AS 5100.4 standard has recently been updated. Are you able to elaborate on the key amendments and how they support sustainable bridge design? Thanks, Mark.
So AS 5100.4 has been quite progressive in that it's incorporated into the standard new generation high performance spot bearings and also the new generation of spherical bearings. It's to accommodate, as I mentioned, to facilitate the use of those bearings. The contact pressure between an attachment plate and the mortar pad or concrete subgrade has been upgraded to allow those higher pressures used in the bearing design to be accommodated. To make better bearing selection, we've clarified the movement range that elastomeric bearings have been designed for, and also deck joints. The movement range where we just design for SLS braking forces. Those clarifications should lead to better bearing and deck joint selection. Also, it's mandated attachment plate, so bearing replacement, hopefully bearing replacement can be carried out quicker, and the standards incorporated provisions for reasonably comprehensive provisions for modular deck joints.
Thank you. And you've sort of covered this, but Mark, we have a question. How do these standards guide engineers in balancing sustainability with practical, cost-effective design solutions? Thanks, Mark.
So the standard recognises the high cost of trying to of bearing replacement and also of deck joint replacement, and so it provides quite conservative provisions. Say for modular deck joints, the cost of replacing a modular deck joint is very large, and the disruption on the road network is very significant. So it's adopted quite conservative design parameters for design provisions for modular deck joints, and so the appreciation has to be that that the actual road network disruption costs for say deck joint replacement is very high. So the standard encourages conservative design provisions.
Thank you, Mark. I'd like to move on to talk about environmental impact and sustainability. And Mahesh, bringing you into the discussion, Mahesh, in what ways can engineered bridge bearings and deck joints contribute to reducing the environmental footprint of infrastructure projects? Mahesh.
Yeah, thanks, Amanda. I generally consider bearings and expansion joints indicate the pulse of the bridge. These components indicate how the bridge is behaving under service. Engineered bearings and expansion joints ensure that the bridge expands, contracts, and transfers load safely and efficiently, thus ensuring that there are no locked-in stresses which the bridge has not been designed for. Engineered solutions also ensure that there are no defects induced in the bridge due to the seizing of bearings or expansion joints. Having quite a number of bridges and in a few of them I noticed the failure or seizing of the bearings that basically leads to buildup of stresses and then eventually leading to cracking or deformation of the elements, which then requires temporary closure, repair, maintenance, and all these lead to non-serviceability of the bridge for a short period of time, and also requires the use of equipment to access the bridge for inspection, repair. All these eventually lead to environmental impacts owing to could be lane closures, traffic diversion, use of materials like chemicals for repair, leading to requirement for a more frequent inspection and maintenance regime.
Thank you, Mahesh. And just now putting a futuristic lens on this topic, Mahesh, how do you see the role of sustainable materials and design practices evolving in bridge construction over the next decade? Thanks.
I think some of the points already were discussed by Mark and Virendra. So what I would like to say here is bearings have evolved over the past century from simple planks being used to transfer the loads to pinion, gear, steel roller, rocker, elastomeric pad, pot PTFE, to now high performance pot PTFE bearings and spherical bearings and also stainless steel bearings. Also, specific mention here I would like to talk about is the HP pot, the high performance pot and spherical bearings, which generally lead to a reduced bearing size, thus basically optimizing the material requirement of the bearings. These also result in reduced substructure sizes, thus optimizing the concrete and steel requirements, which go a long way in optimum utilization of resources. Also of mention here, as Mark had indicated in his presentation, the use of special sliding materials which ensure long range movement cycles, thus minimizing the wear and tear. Mark also mentioned about phasing out of the metal seals in the pot bearings and use of POM seals instead of metal seals. These are the innovation which provides longevity to the bearings. And overall, basically, a well-engineered solution is always provides for the required transfer of loads and movements and optimum use of materials. So this is how things have evolved. I'm sure there is more that is coming up, and there's only scope for improvement, and they are always moving forward and with the innovations.
Thank you. Taking the discussion to the important issue of maintenance and life cycle cost reduction, Mahesh, and then maybe Virendra, you can comment on, are you able to discuss with us the maintenance implications of using engineered bearings and deck joints as opposed to traditional alternatives? Mahesh.
Yeah, I mean, this is another good question because I have been involved in a lot of bridge inspection and maintenance, and these are the things that we come across on a daily basis. What we have noted is on few occasions the purely engineered bearings or expansion joints lead to serviceability issues of not just the bearings and expansions, but also a larger issue of serviceability of the bridge substructure or superstructure. As mentioned earlier in my answer to the previous question on environmental, there is this built-up stresses leading to cracking and deformation of structural elements. So a well-engineered bearing or expansion joint ensures the serviceability of the bridge with the minimum inspection and maintenance regime. To cite a few instances, without naming the specific project or a bridge, some bridges installed with like a pinion gear bearings are enclosed in a grease box to protect the bearing from elements. These require specialized inspection, including access, opening, cleaning all the grease out to expose the bearings and then inspect the bearings. This is a very cumbersome process and costs time and material refill with new grease, maybe traffic closures, lane closures. Exposed roller and rocker bearings, on the other hand, have been noted to have ceased due to corrosion, and again, a heavy maintenance issue. Similarly, poor engineered expansion joints, we have seen that led to traffic hazards such as protrusion of the fingers above the riding surface, which leads to posing a danger to the traffic. Hence, it is important that the bearings and expansion joints are not only serviceable but also comparatively easier to inspect and maintain through the service life of the bridge.
Thank you. Virendra, do you want to add to that?
No, I think Mahesh has quite comprehensively covered all the aspects. I mean, one thing I would like to add is the engineered bearings and deck joints. If we use innovative methods of monitoring integrated with the bearings and deck joints, obviously that would include um, continuous monitoring or infrequent, impromptu or on-demand monitoring of the loads, movements, and rotations in the bearings, or movements and vibrations in the deck joints. That would certainly reduce a lot of manual inspection and maintenance costs. And Mageba has been at the forefront of integrating those new technologies into the bearings and deck joints.
Yeah, thank you. Thanks, Virendra. And just staying with you for now, just talking about what metrics or indicators should be used to assess the life cycle cost benefits associated with specific bridge components. Are you able to talk about that a little bit, Virendra?
Sure. Obviously, the key criteria that any bridge designer should look at while selecting the bearings or deck joints. Let's start with the bearings. The bearings, they need to comprehensively consider all the load requirements or movement requirements. Um, they should be they should be effectively interact with the structure for proper facilitation of or proper transfer of those loads, proper releases of the fixities, etc. At the same time, they should be durable. So the corrosion protection treatment, the materials used to construct these bearings should be well tested and proven for their longevity and the minimal maintenance and inspection requirements. Um, Ease of replaceability, ease of installation, and ease of maintenance if required should be the key metrics of bearing design and selection. Mark and Mahesh, you would like to add something to that?
No, that's fine. Thanks.
I think you covered all here.
Good. Yeah, thank you. Thank you. Moving on to testing and performance assurance. Virendra, coming back to you and asking what testing processes are critical for ensuring the reliability of bearings and deck joints, and how do these tests influence design choices? Thank you.
Um, Testing, I would categorize testing as the design verification testing that's done after the bearings are manufactured. And another type of testing is the improvement testing, where we continuously improve the materials that are used for fabrication or production of the bearings and expansion joints. The example that I would like to give is going a couple of steps back into Mark's presentation. As the new standard evolved, we have now included the high performance pod bearings, advanced spherical bearings, and also the next generation modular joints. So all of these have been improved over several years of research and development in the back end, by utilizing or trying and testing new materials that would wear less, last long, and would least maintenance or replacement over the expected service life. Um, Design verification testing, it's quite important to design the bearings and deck joints as per the guidelines into the code. But at the same time, it is also quite important to verify whether those uh, bearings that are designed are then capable of taking those loads. Mageba has a state-of-the-art, purpose-built test facility that is also accredited by NATA in Australia, to test the bearings to verify their anticipated performance based on the design requirements and the project requirements. And it's quite critical ensure that the testing is done on the appropriate number of samples to ensure the quality assurance across the entire batch.
Thank you. Thank you for that. If we think about pre-design considerations for bearings and deck joints, Mahesh, why is it crucial to factor in the design of bearings and deck joints early in the planning phase rather than treating them as standard components? Mahesh, your view.
Yeah, thanks, Amanda. Yeah, this is a good question because this is something that has evolved over the period of actually the days like the bearings and expansion joints were the last one to be considered in a bridge design, which more often results in the last minute few changes in this on-site or modifications in the structure to ensure that the bearings and expansion joints fit in. So an early involvement with these components, and these are crucial components, as I mentioned before, and these are basically the pulse of the bridge, and then so it can't be ignored as minor components. Most often, it's engineers think that it's a superstructure and substructure, but then the expansion joints and bearings come in last. But no, I think now it has evolved, and with the innovation and with the involvement of the bearing manufacturers like Mageba early in the phase, it ensures that the bearings and expansion joints are catered for and accounted in the design in the superstructure or the substructure, and the sizes are such that they fit in within the substructure and superstructure elements, and there is no requirement for a last minute change on site or crucial period of time of construction, which most often generally compromises quality and serviceability of the bridge. So yeah, I mean that's what I would think is the factors to be considered planning earlier.
Thank you. Narendra, do you want to comment on that?
No, I think Mahesh has quite comprehensively covered it all.
And bringing the engineers in is, Mahesh, what challenges do engineers face when pre-designing these components, and how can these challenges be mitigated? Mahesh.
Again, as I mentioned, mitigation is possible through early involvement and accounting for all those the designs or the elements available in the market, like the HP pot bearings or spherical. An early decision on that is important so that the superstructure or the substructure is sized up to accommodate the expansion joints. So I would say currently with the available technology and companies like Mageba who are forthcoming and helping us out, I think these challenges are easily mitigated if they are involved in the early stages, are accounted for in superstructure and substructure rather than a late thinking after the fact.
Thank you. Thank you for that. Before I ask Mark to come in about real world applications, I just want to focus a little bit more on future trends in bridge design and sustainability. And Virendra, keen to know that with these emerging technologies and sustainability initiatives, what are the future trends you anticipate in bridge design that could further enhance durability and reduce life cycle costs? Thanks, Virendra.
Um, as I briefly indicated before, integration of monitoring and sensing devices into the bearings is quite a trend at the moment, and it should be. It is probably a little bit underrated at this stage. I mean, if we take an example of the cars that we drive today and compare them against the cars that we used to drive 10 years ago, 10 years ago, if someone would have said, your car dashboard will tell you whether your tire pressure on the rear passenger side is reducing, it would have been a height of imagination. But today it's the reality. The same thing is happening with the bearings. So today we can design the bearings that could actually monitor the load that they're experiencing, rotations that they're experiencing, and movements they're taking up. The engineers, the asset managers and owners can sit into comfort of their office, log into the computer and check in real time what those bearings at deck joints are doing at the moment, rather than driving some hundreds, sometimes thousands of kilometers away from their their station to the structure and see if everything is wrong. These monitoring systems can also be integrated with the alert mechanisms to alert the asset owners and managers to look at it when something is not wrong, right. That way they reduce the number of visits required to the site. This way, saving the fuel, the cost, and the time, making the maintenance and maintenance of these structures quite cost effective and sustainable.
That's great. And, you know, the changes for the engineers. So for the engineers, how do they prepare Virendra to adopt and implement these changes effectively in their projects?
I think key to that is engineers should first know about these issues, and I think not issues about these advancements and what's available out in the market. And I would like to thank Engineers Australia and the Standards Australia to make sure everyone is aware of this through the programs like this Thought Leader series and so on. But at the same time, it's also critical that the engineers do engage during the early design stages with the bearing manufacturers, expansion joint manufacturers, to find out about these and plan how these can be incorporated into their structures more cost effectively.
Mm, mm. That's good. And, you know, as I say, you know, Engineers Australia through the Thought Leaders series hope that we'll be able to talk about this more. And Mark, moving on to real world applications and case studies. Mark, in your view, are there any notable projects where innovative bearing and joint selection have successfully improved the sustainability and longevity of a bridge? Thanks, Mark.
So the project that I'll mention is the viaducts on the new Hunter Expressway. So these are match cast segmental bridges built by Balanced Cantilever Construction using an overhead truss. So this was the first time in New South Wales the new generation spherical bearings were used. The footprint of the pier head of these bridges, while large, there's a lot of that it needs to accommodate the permanent bearings and lots of shims and jacks and tie downs. So the incorporation of the new generation spherical bearings, which are more compact than the older pot bearings, was a good innovation. And also spherical bearings have a high rotation capacity. So if you do need to tilt the bridge cantilevers during construction to improve alignment, they are they're the best bearing to select. Those bridges were also in a mine subsidence zone and built across old board and pillar mine coal mines. The voids were filled up with cement fly ash grout, which eliminated most of any potential vertical deflection, but the bridges were subject to quite large far field horizontal movement effects. So with those bearings were designed to accommodate predicted quite large predicted horizontal movements. So with the more compact bearing, that meant the slide plate could be more compact. And also on that bridge, on those bridges, there were 3 bridges. The use of modular deck joints, which can accommodate longitudinal, transverse, and vertical movement, were the best choice.
Thank you, Mark. And I think you've covered some of this, but there is a lot of interest in what lessons from these projects could inform best practices for future bridge design. Thanks, Mark.
So look, I think the lessons from projects is you need to make good bearing selection, and the code, the standard is progressive, and it's got these new generation of bearings. A lot of other existing bridge codes don't have any specific mention of these bearings. Look, one thing I would like to mention as well is that AS 5100.4 is not a bridge bearing design code. It does provide comprehensive rules for elastomeric bearings, but for the other types of bearings, it just provides the primary design and fabrication details. The best bridge bearing design code is actually a European code, EN 3037, in 11 parts. But look, it's quite old now. Most of the new progressive development in terms of bearing types and things is being done through a European technical approval process. So if you do need to, bridge engineers mainly just need to provide a comprehensive and correct bearing performance parameters in the schedules. They need to select the correct standard elastomeric bearing. But if you do need to look at elements of the design of the bearings, then you can look at EN 3037 or the European technical approvals that the manufacturers, the bearing suppliers, develop. So, yeah, I think that's it.
Thank you, Mark. That's great. Just moving on with you, Mark, staying with you to stakeholder and regulatory alignment. And this is a pretty big question that's coming your way, Mark, but how can engineers and other stakeholders align on the need for sustainable choices, especially when they may involve higher initial costs? Mark.
So the standard mandates that look, by setting a notional design life of 50 years, which I've given a case for elastomeric bearings in particular could last a lot longer than that. And look, pots and sphericals, provided any corrosion protective treatment is maintained, they should also have a design life substantially longer than 50 years. But by setting the design life at 50 years, we're mandating the requirement that bearings be designed to be replaceable, and also that the standard encourages that there is suitable access to be able to inspect bearings and also deck joints. In particular, for modular deck joints, there's a requirement for a chamber under the deck joint so that you can access, inspect, and maintain those deck joints.
Thank you, Mark. That's great. And just staying with you, Mark, in your view, how responsive is the current regulatory framework to the challenges of sustainable bridge design, and what improvements would you like to be made? Mark.
So I think the provisions in the standard are aimed at achieving a sustainable income. It makes no sense that a whole bridge is taken out of service or have service curtailed due to the failure of a relatively minor component, such as a bridge deck, such as a deck joint or a bearing. So, look, I think the standard encourages good bearing selection and deck joint selection, and to minimise maintenance obligations, or to maintain the structure and operation.
Thank you, Mark. And thank you to all our panelists. It's been a great discussion and we've covered a lot in a short space of time. So please don't forget that this webinar is recorded and it's available on Engineers Australia's YouTube platform and also on EA On Demand, where it'll be there for 6 months. It's now your turn to get involved and we're going to go into our Q&A. And as said before, if you could please direct your questions via the YouTube chat box and who your question is for. Thank you for everyone who submitted questions whilst registering for this webinar. And we might kick off with some of those. So I'm going to start, Virendra, with you. And we've got a question that's coming from Hugo, who is watching from Queensland. Hugo is asking you, Virendra, I'm interested in how to define informed early decision making.
Thanks, Hugo. Very good question, and obviously key to make the early decisions for the longevity of the structure. The answer also lies into your question, informed. Now, how do you get informed to make the early decision? Obviously, to engage the stakeholders. Who are the critical stakeholders in the process? Bridge designers, obviously the primary one, bridge owners, asset owners, and asset managers. At the same time, the bearing manufacturers or deck joint manufacturers. Once all of these are involved into the early phase of the design, everyone is aware of the possibilities, what is possible and what is not possible. Everyone is aware of what can be expected and cannot be expected. That way, the bearing design, the joint design can be customized to suit the structure and the structural demands and the performance demands over the life of the structure. And that's the key to make the informed decision.
Thanks, Virendra. Mark, we've had a question that's come in from Nicola, and Nicola is watching from Victoria. Good afternoon to you. Asking, how do we ensure with new types of joints that in case of natural disaster or accident, there will be minimal damage to the bridge or just a segment of the bridge? Thanks, Mark.
So I guess I don't know about new types of joints. I would have thought the joints that we currently prescribe will be in use for many years to come. But look, I guess this question looks at earthquake and braking movements and stuff. So we think we've reached the right balance with the deck joint movement requirements that deck joints are designed for, and as I mentioned, the expectation is, say, under under braking events and things, a strip saw joint can close up or overextend without damage to the joint or the adjacent segment. There is a question in terms of for other types of joints, there's a requirement that the joints be designed for SLS braking movements. There is a question about movements due to earthquake. So same as you can get pounding between buildings under earthquake, you could get pounding between bridge deck modules. The standard doesn't address that specifically in terms of if you had a bridge on elastomeric bearings and you get very large earthquake movements, then I guess there is the possibility for finger plate joints, say, that there could be damage to the joint. We consider, I consider that damage would be fairly limited, and the operation of the bridge could be re-established quite quickly by putting down a road plate until repairs are carried out. But look, it doesn't specifically address the movement requirements of deck joints for due to earthquake. One thing I will say as well, though, if you pick a joint that's way oversized, say for a strip seal joint, then and so that the joint never opens up, then there's a good chance that what will happen is the glands in the joint will fill up with sediment and dirt, and then when the joint closes, there's a high risk that you'll damage the seal. The strip seal joints are determined on the basis that from time to time they do or should be selected. So from time to time they do sort of fairly well open up, and then the gusts from passing traffic will clean the joint. So picking a joint that's way oversized could lead to additional maintenance problems. So I hope that's provided a bit of a guide. Thanks.
Yeah, thank you, Mark.
Sorry, Amanda, may I add something to Mark's answer?
Absolutely, please do.
Yes, so Nicola and whoever else has this question, I would invite you to visit Mageba website and search an expansion joint with fuse element. So Mageba have devised a fuse element that's incorporated or integrated into the modular deck joints. In case of earthquake, for example, where the bridges are expected to close or open more than their anticipated service movements, these fuse elements pop up, and they're relatively easy to fix temporarily so that the emergency and the rescue vehicles can pass on, and this also ensures that the damage is limited. Anyone who wants to know more about this, you can contact me or anyone from our Mageba team. Thank you.
Thank you for that, Virendra. Mahesh, we've had a question from Subodhan, who is watching in Queensland. Good afternoon to you, asking you, Mahesh, how do you improve bridge design to reduce maintenance time and cost for the bridge bearings, inspections, maintenance, replacement? It is well known some old bridges have bearings positioned that are not easy to access for inspection, maintenance, replacement. At present, how much design has improved on this matter? Mahesh, thank you.
Okay, good question, Mr. Gordon. Thanks for that. As mentioned before, the choice or selection of the right bearing or expansion joint is the first step that the engineer should take. And towards this, the early involvement with the bearing designer or manufacturer is the key. As we mentioned, there are quite a number of engineered bearings and expansion joints that are available in the market, and constantly being innovated and improved upon by companies like Mageba, which basically ensure that the right kind of bearings or the expansion joints are chosen for the bridge, and they are capable of carrying the intended loads or movements. So the bridge basically has to cater for the bearing sizes and joints, ensuring that there are no, as I mentioned before, on-site or last-minute unplanned adjustments required that may eventually compromise on the quality or the serviceability of the bearing. Designing for future jacking of the bridge is another key aspect that should be looked at in the design phase, and drawing should typically indicate the intended design jack location. As Mark had alluded before, maybe 50 years is what the bearings may require to be replaced. So that's something that if we can ensure in the initial design phase and see where the jack should be and accommodate them, and future provision for those are made and designed. This will ensure that there is no scaffold required or fixtures to the substructure, which is after the fact that when the bearings are to be replaced, then again causing detriment to the structure. This, if we can ensure these before at the early design stages, these go a long way in ensuring that there is, minimal or no hindrance to traffic or serviceability of the bridge whenever there is a requirement for the maintenance. One typical thing is access inspection of pathways at abutments. These are typically mandated nowadays by many of the transport or state agencies. So these are the things that the designer should look out for and cater to at the early design stages.
Thank you. Thank you for that. Mark, we've had a question that's come in around construction phase considerations regarding installation. And this question's from Philip. Philip's watching from Queensland, asking you, Mark, during at what point is a bearing too damaged to use, i.e. due to pinching or bearing rolling, lifting, dry versus wet landing, epoxy considerations? Thanks, Mark.
So, so with elastomeric bearings, they can sustain pretty major damage and still remain operational. So, you know, you can have splits, you can have delamination of the rubber from the steel plates, and they'll still continue to operate satisfactorily in most circumstances. So there's normally no urgency to replace elastomeric bearings. The other so look, the case that is quite critical is the on older style or conventional pot bearings where Teflon was used as a sliding surface. The protrusion of the Teflon from the backing plate is quite small, 1.5 millimeters. And over time, with the accumulated slide distance that the bearing undergoes, the PTFE will wear with time, and there's a possibility that the bearing will seize, and that is a reasonably urgent requirement that defect that should be fixed, because the structure is no longer operating as it's intended if the bearing seizes. And look, for the case where there's extrusion of rubber from the pot, again, that normally is an urgent consideration, and the bearing can continue to operate for quite a few years after extrusion of the rubber has occurred. But look, over time, the rubber disc will reduce, and the bearing will compress more than will compress, and that needs to be addressed. I'm not quite sure what you mean by dry versus wet landing. For epoxy, for elastomeric bearings, there's a requirement that elastomeric bearings are not fixed in place by an epoxy adhesive. The trouble is, in those cases, that bond can break, and then you normally end up with a mirror smooth surface on the epoxy for the the elastomeric bearing can then slide or walk out of position. So there's a requirement that elastomeric bearings aren't fixed in place. The example I showed you with the so elastomeric bearings are normally put on an unconfined cement mortar pad, and that top attachment detail I showed you, that the tapered epoxy mortar pad is pre-molded to the steel plate, and that then is paste epoxies put on that so that there's no gaps when you bolt the attachment plate to the soffit of the girder. But look, if you see a bearing, an elastomeric bearing with a shear incline in it, that's completely normal operational behaviour. But there's a limit that it doesn't exceed half the total rubber thickness.
Thank you, Mark, for that. Mahesh, we've had a question that's come in from Abdul, asking you, Mahesh, how much is the cost difference incorporating the sensors monitoring devices in bearings deck joints as opposed to without these technologies? Thank you for that question, Abdul.
That question, Abdul. These are not costly in the overall scheme of things when you look at it or incorporate them during the design phase or during the construction phase. And if these elements are procured with these devices installed, the overall cost differential will be like between 10 to 20%, which will look at it from a long-term or lifetime cost of the or serviceability of the bridge or the component. It's very minuscule, because but whereas these things, if they are incorporated very early and they have been during the bridge construction incorporated, I think it saves a lot of time, energy, and effort, and it's very sustainable practice. So you don't have to go up there, look at stuff, and with all the remote connectivity that is available, and you can sit in the comfort of the office and look at things there, how the bridge or the expansion joint or the bearing is performing. So yes, this is a good question. This is something that should be looked at and more widely incorporated. And I think Mageba is also on the forefront on this. I think Virendra, if you want to add on this.
No, you quite rightly covered, Mahesh, that the 10 to 20% is probably the higher threshold of these additional costs. Obviously, it depends on what detail of monitoring and what detail of sensing you want to go, but I think this 10 to 20% is quite an encapsulating amount.
Thank you. Thank you for that. We are coming towards the end of today's webinar. But on behalf of Engineers Australia, starting with you, Mark, and then Mahesh, and then Virendra, I just wanted to ask, what advice would you give to our young engineers as to broadly, in your view, how can we support them in this field? Mark?
So, look, one thing I see with young engineers is they go, they develop an advanced structural model of the bridge they're designing, and they then take the numbers out of their model and put it into the bridge design, into the bearing performance schedule. So you end up with loads specified to the nearest kilonewton and movement specified to the nearest millimeter. That just unnecessarily complicates everything. You should, in developing your schedule, you should sort of try and rationalize the number of bridge types and round up the loads that bearings have got to be designed for, and the movements they've got to be designed for. And you need to, don't take the exact movement that comes out of your analysis model. There's no real cost penalty. In fact, the standard now says that you need to add an additional 25 millimeters to the movement range of the bearing, and that's to accommodate uncertainty about the temperature of bearing installation. But you should round up and make conservative the bearing performance requirements that you put in the schedule. Don't just take the numbers out of your structural model and put them straight into the and look, the other thing too, in terms of elastomeric bearings, the bearing performance tables are there to help you make a really good bearing selection by looking at those two columns with concurrent with a 0.01 rotation. You can normally pick a suitable bearing just by reference to the table, and then all you need to do then is check your fixity requirement. In a lot of cases, there's no need to do the detailed calculations to actually select your bearing. You can make a good bearing selection in just 5 minutes by looking at the table and making a good selection. And as I say, to avoid problem with gaps and partial contact on bearings, it's good to pick a bearing that has some additional rotation capability. So work from the bottom of the table up. So you pick a bearing that's slightly taller or has thicker internal rubber layers and is not too thin, has a reasonable overhead height, and then that should avoid issues with partial bearing contact.
Thank you. Mahesh?
Yeah, I mean, this is something good which I always encourage even the engineers who are joining the team or not experienced as much as like experts in the field here. As Mark rightly mentioned, yeah, don't just take the numbers of the software and just plonk it in there. There's 1104.5 kilonewton is the required load on the bearings when you're designing a bridge. See what is feasible, what is practicable to put in there, and also challenge the status quo is one thing that I would say to the young engineers. Just don't accept it. Ask questions, ask relevant questions, and see why a particular thing is being done in a particular way. And these kind of thought leader series that Engineers Australia hosts is a good one. Again, where very good questions have come up in the Q&A sessions, which again go to show how the people are interested and how they are keen to learn. Learning is a continuous thing, and never stop learning. Always you are at some point of the curve in the learning curve, so always think that there is things that more to learn, and as long as you are willing and eager to learn from others, that's a good thing. That's what I would encourage.
Great advice. Virendra?
I will keep it quite brief and short. Obviously, desktop research is is quite important, but most critical is engagement. So engage with your colleagues who has more experience in it. Engage with the industry stakeholders like the bearing manufacturers, designers. Engage with the contractors to understand the constructability as well. Engagement leads to the better informed decisions.
Thank you. Thank you for that. And it is all we have time for today. So please join me once again in thanking Mark Bennett, Mahesh Ramamurthy, and Virendra Godke for their time and input. I'd also very much like to thank Engineers Australia's industry partner, Magiba, for their support. As always, if you don't mind, please completing a short feedback form, which is linked in the description box below. We're working on plans for next year, and it helps us make sure we get the right sessions in place. This will be our last Thought Leaders event for 2024. And just to let you know, we've had 112 events and with over 59,000 people registered. It's been a terrific year. We couldn't have done it without you. And thank you for all your ongoing support. And we'll be doing it all again starting in February next year. Thank you again for joining us. Hope to see you at our events next year, and I hope you all have a wonderful festive season. Thank you. Good afternoon.